What happens when the laws of the universe contradict themselves? When reason collides with mystery, and certainty dissolves into silence, the cosmos stretches before us with the appearance of harmony. Stars ignite and perish, galaxies drift like islands upon a dark sea, and the great machinery of physics seems unbroken. Yet hidden in this order are fractures, questions sharp enough to wound the very heart of knowledge. Paradoxes. A paradox is not simply a riddle, it is a rebellion within reality. Black holes consume matter and energy, yet whisper that information can never be truly lost. Quantum particles flicker between existence and absence, standing in two places at once, mocking the boundaries of logic. The universe itself should not have emerged from nothing, and yet here it stands, vast and undeniable. For centuries, science has carved clarity from the unknown. Each discovery a stone in the cathedral of reason, each equation a step toward certainty. But beneath the arches of this cathedral lie shadows that cannot be banished. The paradoxes remain. They are not errors of imagination, nor trivial curiosities to be dismissed. They are warnings that something deeper hides within the structure of reality, something beyond the reach of our present understanding. Physicists do not ignore them. They wrestle with them in equations that stretch the limits of thought, in experiments that probe the smallest scales of matter and the most violent edges of space-time. Yet still the contradictions persist, and so we ask, are these paradoxes cracks in the foundation of physics? Or are they glimpses into a deeper truth, one that waits beyond the horizon of human reason? The story of paradoxes in physics begins not in modern laboratories or in the halls of observatories, but in the minds of ancient philosophers. Long before telescopes were raised toward the heavens, before particles were smashed in accelerators, human beings asked questions that defied reason. Among the earliest was Zeno of Elea, who in the 5th century BCE crafted paradoxes to challenge the very idea of motion. He asked, if one must first travel half the distance to reach a destination, and then half again and again without end, how can motion ever truly occur? His riddles were more than intellectual games. They revealed a fault line between logic and experience, between mathematics and the lived reality of the world. Even then, long before modern science, paradox was a shadow on the path of knowledge. Centuries later, as mathematics matured and natural philosophy transformed into science, paradoxes evolved. Each discovery brought clarity, but with it came contradictions that resisted explanation. It was as if the deeper humanity looked into the workings of the cosmos, the more the universe presented puzzles wrapped in impossibility. To uncover truth was also to awaken paradox. By the early 20th century, physics stood upon the triumph of classical mechanics. Isaac Newton's laws of motion and gravity had ruled for centuries, a foundation so solid that many believed little remained to be discovered. Yet cracks were already forming. The strange behavior of light and the emerging field of electromagnetism hinted at inconsistencies. And when Albert Einstein revealed the theory of relativity, those cracks widened into a chasm. Space and time themselves were no longer fixed but malleable, woven together in a fabric bent by mass and energy. Reality was stranger than anyone had dared imagine. But relativity, as beautiful as it was, carried consequences. Among them lay a prediction that disturbed even Einstein himself: the possibility of black holes, regions of space where gravity collapsed into infinity, where time and causality could vanish. A paradox of existence itself. Yet paradox did not only haunt the vast, it whispered in the realm of the very small. Quantum mechanics, born from the need to explain the strange spectra of atoms and the dance of subatomic particles, challenged the very notion of certainty. In this new framework, particles could exist in multiple states at once, as if reality itself were undecided until observed. Niels Bohr and Werner Heisenberg embraced this indeterminacy. To them it was not a flaw but a feature of the universe. But Einstein resisted. He famously declared, "God does not play dice." To him, quantum mechanics was incomplete, a theory hiding deeper truths. For how could reality be governed by chance, by probabilities instead of laws? The paradox was clear. Relativity painted a universe of order and determinism, while quantum theory insisted on uncertainty and randomness. Two truths, both tested and verified yet irreconcilable. Other great minds wrestled with these contradictions. Erwin Schrödinger, seeking to expose the absurdity of quantum mechanics, imagined his infamous cat, a creature placed in a sealed box, alive and dead at once until observed. It was meant as a critique, yet it became an icon of the paradox itself, a symbol of the unsettling reality that the universe could exist in superposition, a blur of possibilities awaiting collapse into a single truth. For the first time in history, humanity confronted the possibility that reality itself was not absolute, but dependent on observation. And then came Stephen Hawking, standing at the intersection of relativity and quantum mechanics. He turned his gaze toward black holes, those cosmic abysses predicted but resisted by Einstein. Hawking revealed that black holes were not eternal prisons. They could radiate energy, slowly evaporating into nothingness. But this revelation carried with it a devastating paradox. If black holes evaporated, then what of the information carried by the matter they consumed? Was it lost forever, erased from existence? Quantum mechanics declared that information must be preserved. Relativity seemed to allow it to vanish. Once again, two pillars of science collided, producing a paradox so profound that it remains unresolved to this day. The black hole information paradox became a wound in physics, a rift between theories that both cannot be wrong yet cannot both be right. Each paradox carried the same pattern. They did not emerge from ignorance, from a lack of data or imagination. They arose at the edges of discovery, from theories that worked too well to be dismissed. The paradox of motion in Zeno's thought experiments gave way to calculus, reshaping mathematics itself. The paradoxes of quantum mechanics birthed technologies that define the modern world, from semiconductors to lasers. Even Hawking's paradox, unsolved as it remains, has inspired entire fields of research into quantum gravity, string theory, and holographic principles. Paradox, it seems, is not a failure of knowledge, but a guidepost to deeper truths. To stand before a paradox is to stand before a mirror of our own limitations. Einstein's unease with quantum indeterminacy was not simply stubbornness. It was the recognition that something vital was missing. Schrödinger's thought experiment was not only absurdity but revelation. Hawking's equations did not break physics. They revealed its incompleteness. Each paradox whispered that the universe is more profound than any single framework can contain. Scientists have long understood that paradox is the engine of progress. Galileo confronted the paradox of falling bodies against Aristotelian physics. Maxwell's equations revealed paradoxes that demanded the birth of relativity. The clash between Newtonian certainty and quantum uncertainty is not a contradiction to be feared, but a tension that promises a new synthesis yet to come. Paradox does not close the path forward, it opens it. And so paradoxes became milestones in the journey of physics. They marked the limits of what was known, and they pointed toward what must come next. For Zeno, it was infinity. For Einstein, it was time itself. For Schrödinger, the boundary between reality and imagination. For Hawking, the very fate of information in the cosmos. Each paradox was a torch in the darkness, not extinguishing knowledge but illuminating its boundaries. And at those boundaries, science is forced to grow. The discovery phase of paradox is thus not a story of failure, but of revelation. To encounter a paradox is to realize that the world is not yet fully written in our equations, that the cathedral of reason has unfinished chambers, hidden corridors where mysteries still breathe. In the silence of paradox, humanity is reminded that knowledge is not a final destination, but an unending pursuit. Paradoxes do not appear at the edges of ignorance. They emerge at the core of discovery. They are the pulse that tells us the universe is alive with secrets still waiting to be unveiled. For scientists, paradoxes are not merely puzzles. They are wounds in the fabric of understanding. A paradox is more than confusion. It is a contradiction so deep that it threatens to unravel the laws that hold reality together. To encounter a paradox is to face the possibility that the very rules of the universe may not be as unshakable as once believed. And in this recognition lies both terror and wonder. The black hole information paradox stands among the most haunting of these contradictions. Black holes are born from collapse, when a star so massive exhausts its fuel and gravity overwhelms every opposing force. In Einstein's relativity, the collapse becomes unstoppable, crushing matter to a singularity hidden behind an event horizon, a boundary from which nothing, not even light, can escape. For decades, black holes were imagined as cosmic prisons, eternal vaults in which information about matter was trapped forever. Yet Stephen Hawking shattered this picture. By applying quantum field theory to the space near the event horizon, he revealed that black holes radiate faintly, a process now called Hawking radiation. Slowly, imperceptibly, they evaporate. But if they vanish completely, then the information of what once fell inside would be lost. And this breaks the most sacred law of quantum mechanics, that information can never be destroyed. Two theories, both pillars of physics, collide in contradiction. Does information vanish, defying quantum law, or is relativity itself incomplete? The paradox is a crack in the rules of the game, and through it humanity glimpses its ignorance. But paradox is not confined to the vastness of collapsed stars. It also resides in the intimate heart of matter. The wave-particle duality is one of the strangest truths science has ever faced. For centuries, light was debated. Was it made of particles, as Isaac Newton once believed, or was it a wave, rippling through a medium like sound through air, as Christian Huygens argued? The truth emerged in the 20th century, and it was more disturbing than either possibility. Light is both. In the famous double-slit experiment, photons sent toward a screen behaved like waves, interfering with themselves to create patterns of light and shadow. Yet when measured as single particles, they struck one at a time like discrete bullets of energy. The paradox is unavoidable. Light is not wave or particle, but both, depending on how it is observed. Stranger still, electrons and atoms, the very bricks of matter, obey the same duality. The foundation of reality itself refuses to choose. Logic demands an answer. Nature offers only paradox. It was this clash between the mathematical predictions of quantum mechanics and the intuition of human reason that inspired Erwin Schrödinger's famous thought experiment. He imagined a cat sealed in a box with a mechanism tied to the decay of a radioactive atom. If the atom decays, the mechanism releases poison, and the cat dies. If not, the cat lives. Quantum mechanics insists that before observation, the atom exists in a superposition of decayed and not decayed, and so the cat must exist in a superposition too, alive and dead at once. Schrödinger intended this as a critique, an absurdity that highlighted the problem of applying quantum principles to the macroscopic world. Yet the paradox endures. Is reality itself undecided until it is observed? Does consciousness play a role in collapsing possibility into actuality? The question is not philosophical fancy, but a scientific dilemma. A crack in logic so profound it unsettles the very notion of existence. These paradoxes are not errors to be corrected. They are consistent within their own frameworks, supported by experiment and mathematics. Hawking's equations do not fail. The double-slit experiment repeats its impossible result every time. Schrödinger's paradox still reflects the strange predictions of quantum theory that modern computers and lasers depend upon. Each paradox is a scar written into the universe, a reminder that even our most trusted theories are incomplete. To confront them is to feel the ground beneath reason tremble, and this trembling is what terrifies scientists. For physics is built upon certainty. It is the attempt to describe reality in laws so exact that they predict the motion of planets, the behavior of atoms, the birth of stars. A paradox undermines this certainty. It suggests that the laws themselves may not align, that the universe may be governed by rules that contradict one another. To stand before such a contradiction is to face the possibility that human reason may never fully comprehend the cosmos. Yet within this fear lies a deeper truth. Paradox is not a dead end. It is a signpost. The black hole information paradox points toward a theory that unites quantum mechanics and relativity, a quantum theory of gravity that has yet to be written. Wave-particle duality reveals the need for a new understanding of what matter truly is. Not wave, not particle, but something beyond the language of either. Schrödinger's cat challenges scientists to grapple with the boundary between the quantum and the classical, between possibility and actuality. Each paradox is an invitation to look deeper, to ask questions that shake the foundations of thought. It is for this reason that paradoxes inspire as much as they terrify. They remind humanity that the universe is not a finished story, but an unfinished poem, that behind every equation lies a silence waiting to be broken. Paradox is the heartbeat of discovery. It is the moment when certainty collapses, and in the fragments of that collapse new truths are born. And so scientists wrestle with these impossibilities, not to banish them, but to understand what they reveal. Each paradox is a crack in the rules of the game, yes, but also a window. Through those cracks shines the light of a deeper reality, one that has not yet been written in the language of human reason, a reality that waits silent and patient for discovery. The paradoxes of physics did not remain abstract puzzles on paper. They became the targets of experiments, observations, and calculations designed to pierce their mysteries. If paradox was a crack in the laws of nature, then science would shine its light directly into that crack, no matter how unsettling the result. Yet each attempt to resolve the contradictions often deepened them, revealing truths stranger than imagination. One of the most haunting investigations came from the double-slit experiment, a simple design with devastating consequences for human understanding. When a beam of light is directed toward a screen through two narrow slits, a pattern of alternating bright and dark bands emerges. It is the signature of waves rippling and interfering with one another. But when detectors are placed to observe which slit each particle of light passes through, the interference pattern disappears. The photons act as individual particles instead, as if they somehow know they are being watched. The experiment has been repeated with electrons, atoms, even molecules made of hundreds of atoms. Always the result is the same. Reality itself seems to shift based on observation. It is as though the universe waits for a witness before deciding what form it will take. Instead of solving paradox, the experiment sharpened it. Wave and particle, possibility and actuality, existence and uncertainty, all entangled in a single act of measurement. Black holes offered another arena where paradox became deeper through investigation. Stephen Hawking's calculations of black hole evaporation were not idle speculation. They were born from applying the laws of quantum field theory to the curved geometry of spacetime predicted by relativity. In his equations, virtual particles flickered into existence at the event horizon. One particle fell inward while the other escaped outward, creating radiation. Over eons, this radiation would drain the black hole until nothing remained. But Hawking's insight led directly to the information paradox. The universe seemed to demand that information could be destroyed. For decades, physicists have sought to test these ideas. Though direct observation of Hawking radiation remains beyond current technology, the theoretical framework is solid. Particle accelerators and analog systems, such as sonic black holes created in superfluid helium or Bose-Einstein condensates, have been used to simulate aspects of black hole evaporation. These laboratory echoes confirm the mathematics, but they also reinforce the paradox. The question of information remains unanswered, growing more urgent with every refinement of theory. The paradoxes of the cosmos stretch even further, to the very birth of the universe. When astronomers turned radio telescopes to the sky in the 1960s, they discovered a faint hiss of microwave radiation coming from every direction. It was the afterglow of the Big Bang, the cosmic microwave background, relic light from when the universe was only 380,000 years old. Its uniformity was astonishing. Regions of the sky separated by vast distances, too far apart to have ever communicated at the speed of light, showed nearly identical temperatures. This was the horizon problem. How could the universe be so smooth, so uniform, when causality forbade such coordination? The solution, proposed in the 1980s, was cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation could stretch space itself, explaining the observed uniformity. Yet inflation created paradoxes of its own. If it occurred once, could it not occur endlessly, spawning a multiverse of infinite universes? The search for answers in the hiss of ancient light only expanded the questions, as if the cosmos whispered riddles in every frequency. Quantum entanglement was another investigation that turned mystery into deeper paradox. When two particles are prepared in a shared quantum state, their properties become linked. Measure one, and the other reveals its corresponding value instantly, no matter how far apart they may be. To Einstein, this was unacceptable. He called it spooky action at a distance, a violation of locality, the principle that nothing can influence anything faster than the speed of light. Yet experiments beginning in the 1970s, most famously those of Alain Aspect, proved entanglement was real. No hidden variables could explain the correlations. The universe itself allowed instantaneous connections across space, defying the classical view of separateness. Today, entanglement forms the foundation of quantum computing and quantum communication. What Einstein resisted has become an engine of technology, yet the paradox remains. If entanglement is real, What does it say about the fabric of reality? Is the universe itself a web where distance is an illusion and information flows outside the limits of space-time? Time and again, the tools of science, telescopes, particle accelerators, detectors, and equations, have been aimed directly at paradox. Each revealed evidence not of resolution, but of deeper complexity. The double-slit experiment exposed the mystery of observation. Hawking's calculations showed that black holes could not be silent prisons. Cosmic background radiation studies suggested that the universe is far stranger than a single expanding cosmos. Entanglement challenged the very idea of locality. The paradoxes grew sharper, not softer, with every attempt to cut through them. For those who search the heavens and the atom alike, this is the true shock. The more refined the instruments, the more precise the measurements, the stranger reality appears. It is as if the universe resists simplification, offering paradox as both barrier and guide. The deeper the investigation, the more humanity is forced to admit that its knowledge is provisional, its certainties fragile. Paradox remains carved into the foundation of existence like cracks in an ancient stone, and yet it is within those cracks that light enters. For paradox does not end discovery. It ensures it will never end. The double-slit experiment whispers that reality is participatory. Black holes suggest that information is eternal, though hidden beyond our current grasp. The cosmic microwave background points toward a universe far larger than the one visible to us. Entanglement insists that separateness may be an illusion. Each paradox deepens the mystery, but also deepens the invitation to explore. To investigate paradox is to confront the unknown, not with despair, but with reverence. These tools, these experiments, are not merely tests of theory. They are questions carved into the cosmos itself. Questions that echo back with answers stranger than imagination. The universe is not a book already written. It is a riddle in progress. And paradox is the handwriting of the infinite. As the 20th century gave way to the 21st, science achieved wonders beyond imagination. Humanity split the atom, walked on the moon, mapped the genome, and peered into the birth of the cosmos itself. Yet with every stride forward, new paradoxes emerged, multiplying like shadows in the light of discovery. If earlier contradictions were cracks in the foundation of physics, these newer paradoxes threaten to unweave reality itself. One of the most unsettling is the measurement problem in quantum mechanics. At the heart of quantum theory lies the wave function, a mathematical description of probabilities, a cloud of possibilities in which a particle may be here, there, or everywhere at once. But when observed, the wave function collapses. One possibility becomes real, the others vanish. The paradox is unavoidable. Does reality exist independently or only when observed? Experiments confirm the mathematics, but the interpretation remains unresolved. The Copenhagen view, championed by Niels Bohr, insists that the act of measurement is fundamental. Reality does not choose until it is watched. Others, like Hugh Everett's many worlds interpretation, argue that all possibilities unfold, each in its own branching universe. Still others explore hidden variables or pilot waves, desperate to restore determinism. Yet the paradox lingers. If reality depends on observation, then what role does consciousness play? Is the universe, vast and ancient, somehow incomplete without witnesses to collapse its possibilities? The measurement problem is not merely a question of physics. It is a mirror held up to existence itself. Another paradox challenges the very meaning of existence in the cosmos, the Boltzmann brain problem. In the late 19th century, physicist Ludwig Boltzmann proposed that the order of the universe might arise from random fluctuations in a sea of chaos. Over infinite time, even the most improbable states would eventually occur. Applied to cosmology, this reasoning leads to a disturbing conclusion. It may be far more likely for a single self-aware brain to spontaneously form from random fluctuations than for an entire universe to evolve stars, galaxies, and life through natural processes. If that is true, then it is statistically more probable that every conscious being is not a product of evolution, but a fleeting disembodied fluctuation, arising for a moment with false memories before dissolving back into entropy. The paradox is horrifying. If probability favors Boltzmann brains, how can anyone trust their perception of reality? How can meaning survive in a cosmos where order itself may be an illusion? Scientists wrestle with this nightmare. exploring models of cosmology that might avoid it. Yet the paradox remains as a dark specter, whispering that even existence may be a statistical deception. But paradox does not stop at the smallest scales or the depths of thought. It extends to the stars themselves. In 1950, physicist Enrico Fermi posed a question that still echoes across astronomy. If the universe is ancient, vast, and filled with billions of stars older than the Sun, where is everyone? This is the Fermi Paradox. If life arises even occasionally, then civilizations should have had time to expand across the galaxy. Yet the skies are silent. No signals, no ships, no evidence of visitors from the stars. The paradox gnaws at certainty. Either life is unimaginably rare, or civilizations destroy themselves before reaching the stars. Or perhaps intelligence is everywhere but hidden by reasons humanity cannot yet fathom. Each possibility is unsettling. The Fermi Paradox forces the realization that humanity may be profoundly alone or worse, that it is simply one fragile voice in a universe that does not wish to be heard. These paradoxes of the modern era escalate the unease. They do not merely challenge specific theories. They shake the foundations of reality itself. The measurement problem questions whether the universe exists without observers. The Boltzmann brain paradox undermines trust in memory and meaning, suggesting that existence itself could be statistical noise. The Fermi paradox confronts humanity with its solitude, or with the possibility of unseen forces shaping the silence. Together they paint a picture of a cosmos stranger and more uncertain than any myth once told around firelit nights. And still, the paradoxes multiply. Quantum entanglement, once dismissed as impossible, is now harnessed in laboratories, forcing reconsideration of space, time, and separateness. The discovery of dark matter and dark energy raises questions about what most of the universe truly is, and why its expansion accelerates against gravity's pull. The search for a unified theory, a bridge between relativity and quantum mechanics, reveals contradictions at every turn. Each paradox deepens the sense that reality is not what it seems, that beneath the surface of the observable lies a structure alien to human intuition. For scientists, these paradoxes are both burden and blessing. They destabilize certainty, but they also guide the path forward. The measurement problem has inspired generations of experiments, from quantum erasers to delayed choice tests, each one probing the boundary between possibility and actuality. The Boltzmann brain paradox has driven cosmologists to refine models of inflation, entropy, and the multiverse, searching for ways to preserve meaning in the face of probability. The Fermi paradox has fueled the search for extraterrestrial intelligence, driving radio telescopes to sweep the sky and space probes to wander beyond the solar system. Each paradox terrifies because it questions reality itself, but each paradox also drives humanity toward deeper truths. The escalation of paradox reveals something profound. Knowledge does not banish mystery. It multiplies it. The more humanity learns, the stranger the universe becomes. What began with Zeno's riddles of motion now stretches to the silence of the stars, and the possibility that reality itself depends on being observed. The paradoxes of the modern age are not small cracks in the cathedral of science. They are vast chasms, opening beneath the very idea of certainty, and yet they are also bridges, gateways to a deeper understanding that has not yet been written. The mystery deepens. The paradoxes remain, and the universe, silent and vast, waits for humanity to listen to its impossible truths. Paradoxes do not remain silent forever. They demand explanation, and human curiosity is relentless. From the earliest riddles of Zeno to the black hole information paradox, each contradiction has been a signal, an invitation to build new frameworks, new theories, new ways of seeing. Science advances not by certainty alone, but by speculation born from paradox. And so, in the 20th and 21st centuries, the great paradoxes of physics inspired a flood of bold ideas, attempts to reconcile contradictions at the heart of reality. Among the most audacious are multiverse theories. The measurement problem in quantum mechanics, where a particle exists in many states until observed, seems to beg for resolution. One answer comes from the many worlds interpretation proposed by Hugh Everett in 1957. In this vision, the wave function never collapses. Instead, every possibility becomes real in branching universes. The electron goes left and right. Schrödinger's cat lives and dies, Countless realities bloom, each as real as this one, diverging endlessly. The paradox dissolves because all outcomes exist, yet the cost is staggering. If true, the cosmos is not a single unfolding story, but an infinite library of histories, most unseen, all real. Critics argue it is untestable, an extravagant answer to a problem created by interpretation. But the multiverse lingers not only in quantum mechanics but also in cosmology, where eternal inflation suggests endless universes budding from inflating space. The paradox of one universe may only be resolved by imagining infinite others. Another attempt to reconcile contradictions lies in string theory. Where relativity and quantum mechanics clash, string theory offers a bridge. It suggests that the fundamental building blocks of reality are not point particles but tiny vibrating strings. They're different modes of vibration, giving rise to particles and forces. Gravity and quantum theory, once irreconcilable, may both emerge from the same underlying fabric. But strings require more than the familiar 3 dimensions of space and 1 of time. They demand hidden dimensions, curled so tightly they are invisible to human eyes. 10 dimensions, or even 11, woven together in geometries beyond imagination. In this vision, paradox is resolved by expanding reality itself. What appears contradictory in 4 dimensions may be harmonious in higher ones. Yet string theory, for all its elegance, remains speculative. No experiment has yet confirmed its predictions. It hovers at the edge of science and philosophy, beautiful but unproven. Cosmic inflation is another answer born from paradox. The uniformity of the cosmic microwave background, the horizon problem, the flatness of the universe. These riddles cried out for resolution. In the 1980s, Alan Guth proposed that in the first instant after the Big Bang, the universe underwent a phase of rapid, exponential expansion. Inflation smoothed out irregularities, stretching the cosmos to the vast, nearly uniform expanse we observe today. It explains the paradoxes of the Big Bang with elegance, predicting the structure of the universe at large scales. Yet inflation itself raises new paradoxes. If inflation can occur once, why not again? Endlessly spawning bubble universes in an eternal multiverse. In solving one paradox, inflation opens another. The possibility that our cosmos is just one among countless others, forever hidden from view. Some speculations go even further, stepping beyond physics into the philosophical. The simulation hypothesis asks whether the paradoxes of reality are not features of the cosmos at all, but flaws in the code of a vast computation. If advanced civilizations could simulate entire universes, complete with conscious beings, then perhaps paradoxes are simply glitches, inconsistencies in the program. In this view, the measurement problem is not mystery but algorithm. The universe does not resolve possibilities until observed because rendering every detail would be wasteful. Entanglement is not spooky action, but pre-written correlation in the code. To imagine reality as simulation is to transform paradox from physics into architecture, the architecture of a mind beyond our own. It is speculation without proof, yet it lingers, unsettling because it is difficult to disprove. If paradoxes are glitches, then truth itself may be an illusion, but even within mainstream science, interpretations clash like rival philosophies. The Copenhagen interpretation favored by Niels Bohr insists that the wave function is not real but a tool, and that reality emerges only when measured. The many worlds interpretation denies collapse and multiplies universes. Pilot wave theory, revived by David Bohm, posits hidden variables guiding particles along deterministic paths, restoring order beneath quantum uncertainty. Each framework resolves paradox in its own way. Each leaves paradoxes of its own. None commands universal acceptance. The battle of interpretations reveals that even among the most brilliant minds, consensus is elusive. The paradoxes remain not because science refuses to confront them, but because no single explanation is sufficient. This lack of resolution unsettles many. Science has long been the pursuit of universal laws of clarity that banishes mystery. But here, in the heart of paradox, clarity fragments. Relativity and quantum mechanics, both experimentally flawless, refuse to unite. Inflation explains the cosmos yet raises untestable infinities. String theory promises unity, but drifts without experimental anchor. Simulation offers simplicity at the cost of reality itself. No answer is complete. Each is both resolution and question, and yet in this uncertainty lies something profound. Paradox reveals that reality is not obliged to conform to human intuition. The universe may be stranger than the categories of thought can contain. To wrestle with paradox is not to fail but to stand at the frontier of knowledge. The theories and speculations born from paradox are not final truths. They are scaffolds built to climb higher into the unknown. The absence of consensus is not weakness. It is vitality. It means the cosmos has not been reduced to simplicity. It means there are still mysteries vast enough to inspire awe. Paradox ensures that discovery is unending, that the pursuit of truth remains alive. Theories rise and fall. Some will endure, some will be discarded, some will transform. But the paradoxes remain as guides. Multiverse, string theory, inflation, simulation. These are not answers alone. They are reflections of human imagination pressing against the limits of understanding. Each one whispers that the universe is more than equations, more than logic, more than certainty. And so science moves forward, not by solving paradox once and for all, but by embracing it. For in paradox lies the promise that reality has depth still hidden, waiting to be revealed. Paradoxes may be ancient, but the tools to confront them are new. Humanity no longer gazes only with the naked eye or relies on thought experiments alone. It builds instruments of staggering scale and precision. Machines that stretch across continents, telescopes that see back to the dawn of time, detectors that capture whispers from invisible realms. These tools are not weapons to destroy paradox. They are lanterns, shining deeper into the shadows, testing the limits of knowledge, revealing truths stranger than imagination. The Event Horizon Telescope was one such lantern. In 2019, it delivered an image once thought impossible, the shadow of a black hole. By linking radio telescopes across the Earth, the EHT became a planet-sized eye, capable of resolving detail finer than any single instrument could achieve. Its target was the supermassive black hole at the center of the galaxy M87, and there, at the edge of physics, it revealed a glowing ring of light bent by gravity around darkness itself. The paradox of black holes, once a mathematical ghost, became a visible reality. In the years since, the telescope has turned its gaze toward Sagittarius A, the black hole at the heart of the Milky Way. These images are not solutions to paradox, but confirmations of it. They remind humanity that black holes are real, that the information paradox is not an abstract concern, but a question carved into the very structure of the cosmos. The event horizon, once imagination, is now seen. And in that vision, the paradox deepens. If telescopes explore the vast, colliders probe the minuscule. At CERN, the Large Hadron Collider is a ring 27 kilometers in circumference, buried beneath the soil of Switzerland and France. Within it, particles are accelerated to near the speed of light and smashed together in violent collisions. Detectors the size of cathedrals record the aftermath, searching for hidden symmetries and undiscovered particles. The discovery of the Higgs boson in 2012 confirmed the Standard Model, but also sharpened paradoxes. Why does the Higgs field have the value it does, giving mass to matter but not collapsing the universe? Why does the Standard Model explain so much yet leave dark matter, dark energy, and gravity unexplained? Colliders like CERN's are not only engines of discovery, but crucibles of paradox, where contradictions emerge more starkly the deeper humanity looks. Each particle revealed answers one question while birthing many more. Quantum computers represent another frontier. Unlike classical machines, which calculate with bits of 0 or 1, quantum computers exploit superposition and entanglement, operating with qubits that embody multiple states at once. In this way, they are not merely machines when they are laboratories of paradox. They embody wave-particle duality, collapse, and entanglement in hardware. Each algorithm, each computation, is an experiment in the strange rules of the quantum world. Already, quantum processors demonstrate effects no classical computer can replicate. In time, they may simulate black hole evaporation, quantum gravity, or entire cosmological models, probing paradoxes in ways thought impossible. Quantum computers do not banish contradiction. They live within it, harnessing paradox as resource. They are proof that what terrifies also empowers. Beyond Earth, new eyes are opening to the cosmos. The James Webb Space Telescope has unfolded its golden mirrors, gazing with infrared vision into light stretched by cosmic expansion. It peers through dust clouds to watch stars ignite, and it gathers light that has traveled for more than 13 billion years, nearly to the dawn of time. Webb is not only a telescope of beauty, it is a paradox hunter. By studying the earliest galaxies, it tests inflation. By examining exoplanet atmospheres, it probes the paradox of life's rarity in a vast cosmos. Its instruments have already revealed galaxies larger and more developed than expected, threatening to overturn models of cosmic evolution. Like every great tool before it, Webb does not resolve paradox but multiplies it, reminding humanity that the universe is both stranger and richer than prediction. And Webb is only the beginning. Next-generation instruments, from the square-kilometer array to gravitational wave observatories, will widen the lens. The square-kilometer array will map cosmic hydrogen with unprecedented clarity, probing dark energy and testing the structure of the cosmos. Gravitational wave detectors, already catching the tremors of colliding black holes, will listen more deeply, perhaps one day hearing the echoes of the Big Bang itself. Each tool is designed to test paradox directly. Each is a step toward understanding whether contradictions are temporary confusions or permanent features of reality. Yet a deeper possibility lingers. That paradox is not a problem to be solved, but a truth to be lived with. Every tool sharpens vision, but none has erased contradiction. The EHT revealed the black hole's shadow, but the information paradox remains. CERN confirmed the Higgs boson, but mysteries of mass and dark matter endure. Quantum computers embody superposition, but they do not explain why observation collapses it. Webb shows galaxies that should not exist so soon, deepening the puzzle of cosmic formation. Each tool illuminates, but each illumination reveals new shadows. Perhaps paradox is not an error in the rules, but a signature of the rules themselves. Perhaps the universe is not built to be seamless, but to contain contradiction, a tapestry woven from tension. In such a cosmos, science is not a march toward final truth, but an unending dance with paradox, each step revealing beauty as well as confusion. The tools of the present are powerful, but they may never deliver absolute answers. Instead, they will refine the questions, narrowing uncertainty while amplifying mystery. The paradoxes may remain unsolved not because science has failed, but because reality is stranger than resolution allows. And so, humanity builds ever greater machines, raises ever sharper eyes, and dreams ever bolder theories. The paradoxes endure, but so does the pursuit. The Event Horizon Telescope peers into darkness. Colliders split matter into fragments of mystery. Quantum computers turn paradox into power. The James Webb Space Telescope and its successors gather ancient light, whispering secrets across cosmic time. Each tool is both question and answer, both lamp and shadow. The paradoxes may never vanish. They may be the heartbeat of reality itself, and if so, then humanity is not defeated by them. It is guided. For to live with paradox is to live with wonder, and to search in paradox is to stand forever at the edge of the unknown. Paradoxes are more than puzzles of science. They are mirrors. In their glass, humanity sees not the flaw of the cosmos, but the boundaries of its own understanding. Each contradiction is a reminder that human logic, precise and trusted, may not be the language in which the universe is written. Paradoxes are not cracks in reality. They are cracks in perception, the fractures that appear when finite minds attempt to grasp infinity. For centuries, science has illuminated the darkness with laws and equations, drawing order from chaos. It has mapped the stars, weighed the atom, and measured the age of the universe itself. Yet even at the summit of knowledge, paradoxes remain like distant peaks still hidden in cloud. They whisper that there are truths beyond comprehension, that the universe may not be built to yield fully to reason. Perhaps the laws of nature are not contradictions at all, but symmetries so profound that human categories cannot yet hold them. Perhaps what appears impossible is only the shadow of a deeper order, glimpsed from the wrong angle. The scientists who wrestle with these paradoxes know this. They are not kept awake by fear, but by awe. They walk the thin line between certainty and mystery, staring into the contradictions not as defeats, but as invitations. When Hawking contemplated black holes, when Bohr defended the uncertainty of quantum mechanics, when Einstein questioned the dice of the universe, none were paralyzed by despair. They were moved by the recognition that reality is richer than comprehension allows. To stand before paradox is not to fail. It is to confront wonder so vast it bends the mind. Paradoxes reveal humility as the price of knowledge. They remind humanity that it is not the master of the cosmos, but a participant within it. The universe is not obliged to be simple, nor to conform to human categories of thought. Its logic may be alien, its rules unlike any ever conceived. To live with paradox is to accept that knowledge is provisional, that every answer opens deeper questions. It is to understand that science is not a final book, but an unfinished manuscript, written line by line in the language of paradox. And yet, in this humility lies power. For paradox fuels wonder, and wonder fuels courage. The courage to build machines the size of cities, to link telescopes across Earth, to harness quantum uncertainty in computers, to listen for whispers from ancient stars. It is paradox that drives humanity forward, not certainty. Certainty breeds comfort. Paradox ignites discovery. What does it mean, then, for humanity to live in a paradoxical universe? It means to live in awe, to wake each day in a cosmos that resists completion, where every law is both truth and question, every answer both resolution and riddle. It means to face the unknown not with arrogance but with reverence, knowing that even contradiction is a form of beauty. Paradox is not a barrier to understanding. It is the signature of a universe that will never be exhausted, a universe alive with infinite mystery. Perhaps in the end, paradox is not a flaw in the universe at all. Perhaps it is a flaw in perception, the mismatch between finite thought and infinite reality. To the cosmos, there may be no contradiction, only harmony, only order beyond comprehension. The paradoxes that unsettle reason may be illusions born of limited sight, like shadows mistaken for fractures in stone, and so the journey continues. The scientists will go on peering into black holes, colliding particles, and unraveling quantum states. They will continue to chase paradox, not to destroy it, but to live alongside it. For in paradox lies the truest reflection of humanity, a fragile species, daring to question the very rules of reality, humble before the vastness, yet unafraid to seek its secrets. In the silence of the cosmos, paradox endures. It is the abyss into which reason stares, the mirror that reveals human limitation, the flame that keeps the pursuit alive. Perhaps the final truth is this: the universe does not promise to be understood. It promises only to be experienced with awe, with humility, with the courage to ask questions that may never be answered. And so the reflection lingers, haunting yet profound. Perhaps the paradox is not the flaw of the universe. Perhaps the paradox is the flaw of perception, and in that flaw lies the greatest gift of all, the endless wonder of a cosmos that will forever surpass the boundaries of thought.